Hi everyone, my name is Sammah. I'm from Mobileye and the Hebrew University, and I'll be talking about deep reinforcement learning for driving policy. This is joint work with Professors Shai Shalev Schwartz and Amnon Shashua. So before we go into driving policy and deep reinforcement learning, I want us to think about the main motivations behind developing autonomous cars besides the fact that it's a very good way to make lots of money. So the first thing is for comfort. I'm sure most of you have spent a lot of time this morning just standing in traffic and basically wasting your time, feeling frustrated, and you'll be very glad if somebody else did this work for you, freeing up your time. The second thing, and perhaps more important, is the safety part. We as humans make lots of errors. We get distracted, we get tired, we misjudge many things, and hopefully robots are immune to those flaws and could increase the safety on the roads and potentially save many lives. So autonomous driving is a complex problem, and we can separate it into three sub-problems. The first one is the sub-problem of sensing. So given input from sensors and from map, we're aiming to build a picture of the present, of the world that surrounds us, and maintain some sort of sensing state, both in terms of static objects like the lanes and traffic signals, and dynamic objects like other road users, cars and pedestrians. The last part of driving is control, which is basically steering the wheel and pushing the pedals in order to move the car in the direction we desire. Now, we as humans make this transition from sensing to control very naturally. But in the middle, we have a third part, which is driving policy. And that part is about the future. That part is about planning where we want to get to in order to achieve some goals that we have, like getting home or getting there safely or quickly. And once we plan for the future and understand where we want to get to, only then do we control the car and move it towards the desired direction. The first question which we should ask is whether this is an issue at all. I mean, perhaps this is a very trivial thing, and there is no need for very complex algorithms in order to solve it. So, this was taken in Jerusalem, and these are human drivers, not autonomous cars, and I don't think that was very comfortable or safe for the people who were sitting in those cars, and we'll now look at it closely, and there was almost a crash. So we want to avoid that, and human beings seemingly don't do that very, very well. On the other hand, human beings do some amazing stuff, and somehow they manage to this is in Paris, somehow they manage to get along with no evidence structure, and many other road users with seemingly no problem. This is India, and this is much more difficult, and if you pay close attention, you'll see there's a cow crossing the junction, and you should also pay attention not to run over the cow. Now, this becomes very difficult, so I think we're all convinced that it's not a trivial problem. And this piece, I think, says it's in very nice words. It says that the glitch with driverless cars are that they obey the law all the time, without exception. And this may sound like the right way to program a robot to drive a car, but good luck trying to merge into a chaotic, jam-packed highway and so on. And it tends not to work out well. So let's summarize for a second the challenges that we are facing in order to make it work well. So we need to balance between being defensive and aggressive. If we will be too cautious because something bad could happen, well, we might as well stay at home. We need to be also a bit more aggressive sometimes. Another thing is that we need to negotiate our way and communicate with other road users in order to avoid such situations as we saw in the first movie. And we need to understand somehow what are those rules, those unwritten rules of breaking the rules. I mean, we are not supposed to push our way into a packed roundabout, but we do that. And we need to understand when is it okay. And finally, there is lots of uncertainty in the world surrounding us, and we need to know how to adapt to those situations where there might be a kid hiding behind a car and jumping into the road in a few seconds. And this is where the magic 3 words come into the picture: deep reinforcement learning. So when applying deep reinforcement learning for driving policy, there are many challenges specific to this problem, and I will talk about first reinforcement learning without Markovity, and secondly about safe reinforcement learning. So Roy was making most of the work for me, so I will be very brief here. And as we all know, in reinforcement learning, we are trying to learn a policy. And the game is that at each time steps, we observe a state, ST, we choose an action based on our policy, pi, and the environment moves us to the next step. And we get feedback as a reward signal at each time step. Now, a very common model to use for those games is the Markov decision process, or MDP model, which adds in the additional assumption that the next state and the reward are conditionally independent of the past given the current state and the action that we take. Which means that basically, if I know the current state of the environment around me, that is enough. I will not gain anything by knowing all of the past. And this, of course, have several very useful consequences, which introduces the value and the Q functions, and they satisfy some very nice properties, and this gave rise for value iteration and Q learning, very popular, and I'm sure most of you have heard of them. However, the problem is that in a multi-agent setting, such as driving, the Markovian assumption simply doesn't hold. Because in order for it to hold, in order for the state that we observe to be sufficient for us to know anything we could have had we known all the past, we need to encode in the state some stuff like the mood of the other drivers, which is very, very difficult. And because this grows with time, we can our state space will grow and be huge, and making the problem intractable. And therefore, we do not want to assume Markovity, and we adopt an agnostic reinforcement learning setting where the optimal policy is not necessarily a function of the current state. But this rules out using a value function or Q function. And therefore, when we look at the most common approaches for reinforcement learning, we need to rule out value-based and model-based learning. We can use imitation, which is basically to try to imitate an expert or a real driver in our case. This could cause different problems, like that small errors can add up over time and become big errors. And this leaves us with considering direct policy optimization. So again, Roy was discussing this earlier, but our objective is to maximize the reward over sequences of states and actions with our policy. And the nice thing is that we can obtain an unbiased estimate of the gradient of this objective. And actually, this policy gradient theorem was known a long time ago, but we have just observed that they never use in the proof the Markovity assumption. So it basically works for a non-Markovian setting just as well. Let's see now the first results after our first try using this method. So the white car is trying to change lane to the left, and it hesitates, and it goes back, and suddenly it just decides to go for it, and it's very, very close. And again, I wouldn't want to sit neither in the black or the white car. And this brings us to the second part of the talk and of the problem, and that is the problem of safe reinforcement learning. And in most cases, safety in many learning problems, safety is not such a great issue as it is with autonomous cars, where it's actually a matter of life and death. So it must be taken care of. And why basically safety is a problem? So recall that the objective is to maximize the expected reward of our sequences of states. So let's say that usually the reward is between -1 and 1 for typical events. For example, if we succeed to move to the other lane, or overtake another car, or yield to the traffic, or whatever. But there are very, very rare events, such as crashes, which happen with very, very low probability. In order for them to make any impact on the expected reward, we will need that reward of those rare incidents to be extremely large. And this will lead to a huge variance problem in the learning process, because our gradient estimate our estimator has a huge variance. So this makes it very difficult to ensure that a learned policy will be safe. Our solution to this problem is by decomposing the policy, which, as we recall, is a mapping from states to action, into two sub-policies. The first one we denote by pi comfort, and it is parameterized by theta. This is a policy which we learn, and we map from states to some domain D, which encodes desires, some semantic desires for us. Actually, very similar to the options mechanism. And later on, we compose this output into a second function, pi safety, which, as you note, is not parameterized and is not being learned. And that function takes all those desires that we have and maps it into real actions. So what is this safety part? So as I said earlier, it takes those desires, constructs an optimization problem under hard constraints over safety. And those constraints could be like keeping safety distance and not driving above speed limit and many things like that. And we solve this optimization problem under those constraints, thus ensuring that the resulting action will be safe. So a few examples for some semantic desires which we can learn. One of them could be the desired gap which we want to enter when we lane change, or given semantic meaning to different road users. So for example, saying those cars, I want to give the right of way to them, those two I don't want to, and I want to take my way and not let them pass. Another thing could be semantic meaning for pedestrians. So for example, those two people are standing and are irrelevant to the second lane, and I can take an offset from them. However, the guy behind, he's crossing the street, and I must stop in front of him in order to let him complete his move. And now we can look at a few more examples, this time with a safety mechanism above the learned policies. And the red cars are trying to move to the right, the white cars are trying to move to the left, and they, of course, don't know the color they are colorblind. So they need to understand what the other guys are doing, not based on the color, but based on their actions. And we can see how smoothly they move, and they wait, and they allow smooth transition. Another example here, the car on the left accelerates to get into a desired gap. And this is all under safety constraints. And the last one, also, I think, very, very nice. So now, getting back to reality, this is exactly the same, right? Those two cars are trying each to get to the opposite direction, and they don't do it very well. So we can hope that indeed, by approaching autonomous driving, we can also get more comfort in our transportation, and more important, more safety, and be better than human beings. So to summarize, driving is a multi-agent game which poses many challenges. The first of them is non-Markovity, which we address by using an agnostic RL approach, and we show that the common methods do not rely on Markovity assumption. And the second one is safety, which we address by decomposing the policy into a comfort policy and safety policy, which is not learned. And this way we can ensure safety while enjoying the many benefits which we can get from reinforcement learning and machine learning. And those are generalization to and adaptivity to many scenarios, and human-like behavior, which balances defensiveness and aggressiveness, helps us negotiate and communicate, and finally helps us understand and follow those unwritten rules of the road. Thank you very much.